Today we're going to explore one of the most fascinating mysteries in acoustic physics, the unexpected behavior of bubbles in sound fields. Let's start with what we expected to happen based on classical acoustic theory. When you create a standing sound wave, you get regions of high pressure called antinodes and regions of low pressure called nodes. This diagram shows a standing wave pattern. The red lines mark pressure nodes, the blue lines mark antinodes, and the curves show the pressure distribution. Classical acoustic theory tells us about something called the primary Bjerknes force. This is the force that acts on a bubble in a sound field. The primary Bjerknes force equals negative the time average product of bubble volume and the pressure gradient. What this equation tells us is that bubbles should be pushed toward pressure nodes, the regions of minimum pressure variation. When a bubble oscillates near its resonance frequency, this force becomes particularly strong. The force is approximately proportional to negative 4 pi times the bubble radius cubed times the pressure amplitude divided by wavelength times sine of kx. You might wonder, where does this force come from? Let me explain the physics. When sound passes through water, bubbles expand during low pressure phases and contract during high pressure phases. The key insight is that the bubble's volume is larger when it's at a low pressure location, so it experiences a net force toward lower pressure regions. This diagram shows how a bubble is larger in the low pressure region and smaller in high pressure, creating a net force toward the pressure node. Based on this understanding, classical theory made a clear prediction about bubble behavior. Bubbles should migrate to pressure nodes and remain stationary at those positions. This is single-body dynamics. Each bubble moves independently. The theory assumed that bubbles don't significantly interact with each other. Each bubble responds only to the external sound field. The migration timescale is approximately wavelength squared divided by the Bjerknes velocity. For typical conditions, this might be milliseconds to seconds. But when experimentalists actually looked at microbubbles in standing sound fields, they saw something completely unexpected. Instead of settling at nodes, microbubbles were observed orbiting around one another in complex patterns. This diagram shows bubbles forming a ring structure and orbiting around a central point near a pressure node. This was completely unexpected. Bubbles arranged themselves into chains, with each bubble oscillating in phase with its neighbors. The motion wasn't random. Bubbles traced out reproducible trajectories including circles, ellipses, and even figure-8 patterns. Most striking of all, they did not simply settle at the pressure nodes as every textbook predicted they should. Why was this such a shocking observation? It contradicted fundamental assumptions. Classical acoustics is based on linear wave equations. If each bubble responds independently to the sound field, their motions should not be coupled. The primary Bjerknes force only describes how one bubble responds to an external field. It says nothing about how bubbles interact with each other. Where was the energy coming from to sustain these orbital motions? In a purely dissipative system, you'd expect motion to decay, not persist. The resolution to this mystery came from recognizing that bubbles don't just respond to the external sound field, they also generate their own acoustic fields. An oscillating bubble is itself a source of sound waves. It radiates pressure waves into the surrounding fluid. The scattered pressure field from a bubble falls off as R0 cubed omega squared divided by R times the oscillation amplitude times cosine of omega t minus kr. This means each bubble creates its own local pressure field that can influence nearby bubbles. This leads us to the secondary Bjerknes force, the force between two oscillating bubbles. The secondary Bjerknes force equals negative the time averaged gradient of the pressure field from bubble 1 times the oscillating volume of bubble 2. Unlike the primary force, which always pushes toward nodes, the secondary force can either attract or repel bubbles depending on their phase relationship. The magnitude scales as density times omega squared times R1 cubed times R2 cubed times the oscillation amplitudes divided by distance squared. This raises an important question. When do bubbles oscillate in phase versus out of phase? When the driving frequency is below the bubble's natural frequency, bubbles oscillate in phase with each other, leading to attraction. When driven above resonance, bubbles oscillate out of phase, leading to repulsion. The resonance frequency equals 1 over R0 times the square root of 3 gamma times ambient pressure divided by density. Let's put in some realistic numbers to see when these secondary forces become important. Let's consider a bubble with radius 10 micrometers. That's 0.01 millimeters. R0 equals 10 times 10 to the negative 6 meters. Its resonance frequency is approximately 2 pi times 300 kilohertz. That's in the ultrasonic range. Now let's say two such bubbles are separated by 100 micrometers, which is 10 times their radius. The ratio of secondary to primary force scales as R0 times oscillation amplitude divided by wavelength. If the oscillation amplitude is about 10% of the bubble radius, which is typical for moderate driving, the amplitude is about 1 micrometer, and the wavelength at 300 kilohertz is about 5 millimeters. This gives a ratio of about 2 times 10 to the negative 9. Wait, that seems very small. But this calculation is actually misleading. Let me explain why the secondary force matters more than this suggests. Here's the key point. Near a pressure node, the gradient of the external pressure field goes to 0, so the primary force vanishes. However, the secondary force between bubbles does not vanish at the node. It remains strong because it depends on the bubble-generated fields, not the external field. At the node, the primary Bjerknes force approaches 0, but the secondary Bjerknes force does not equal 0. This is precisely why secondary interactions dominate once bubbles have migrated close to pressure nodes. Now we can understand the mechanism behind the self-organization of bubble structures. First, the primary Bjerknes force does its job and brings bubbles to the vicinity of pressure nodes. Once near the node, the primary force weakens dramatically and secondary forces between bubbles become dominant. The bubbles lock into synchronized oscillations, and the secondary forces create stable orbital configurations rather than allowing the bubbles to settle. This shows how bubbles arrange around a node with mutual secondary interactions, creating a stable pentagonal pattern. You might ask, what about energy? Where does the energy come from to sustain these motions? The external acoustic field continuously pumps energy into the bubble oscillations. This is not a conservative system. Energy is dissipated through viscous damping at the bubble surface and through acoustic radiation into the far field. In steady state, the rate of energy input from the driving field balances the dissipation, maintaining persistent orbital motion. Power input equals power loss to viscous dissipation plus power radiated acoustically. We can describe this system mathematically as a set of coupled, nonlinear oscillators. Each bubble obeys an equation, R double dot plus omega 0 squared R equals the driving force, plus the sum of interaction forces from all other bubbles J. This is fundamentally a mini-body problem with nonlinear coupling between oscillators. No wonder linear theory couldn't predict it. The coupling terms depend both on the distance between bubbles and their relative phase of oscillation. What kinds of patterns can emerge from these nonlinear coupled dynamics? One common pattern is stable rings, where bubbles orbit around a common center like planets around a star. Another pattern is linear chains, where bubbles align in a row with regular spacing. At higher bubble densities, you can get crystal-like lattices, with bubbles arranged in two-dimensional hexagonal arrays. Here we see two common patterns. On the left, a ring configuration with 6 bubbles, and on the right, a hexagonal lattice structure. Let me give you an analogy that might make this more intuitive. Imagine couples dancing at a party, and there's a special focal point in the room where the music is best. Everyone wants to be near that focal point. That's like the primary Bjerknes force bringing bubbles toward the node. But the couples also need to maintain distance from each other so they don't collide. That's like the secondary forces between bubbles. The result is that couples end up orbiting around the focal point in a coordinated pattern, just like the bubbles. This discovery has profound implications for practical applications. Understanding secondary forces enables precise acoustic manipulation of microparticles, cells, and even nanostructures. In medical ultrasound, microbubble contrast agents don't behave as independent scatterers. Their collective behavior affects image quality. In sonochemistry, where ultrasound drives chemical reactions, the spatial patterns of bubbles directly influence reaction rates and product yields. Understanding bubble interactions helps predict and control cavitation damage in everything from ship propellers to medical devices. This story teaches us an important lesson about the limits of linear approximations. In linear acoustic theory, bubbles are treated as passive tracers that simply respond to the imposed field. In reality, bubbles are active participants, they modify the acoustic field and interact with each other through these modifications. The fascinating collective behaviors we observe emerge from nonlinear interactions that linear theory completely misses. Let me briefly mention the historical development of this understanding. In the early 1900s, Wilhelm Bjerknes first described the primary acoustic forces on bubbles. The theory of secondary Bjerknes forces was developed in the 1970s and 80s through the work of several researchers. The first clear experimental observations of complex bubble self-organization came in the 1990s and 2000s with improved imaging techniques. In recent years, sophisticated computational models have been developed that quantitatively reproduce the observed patterns. Despite our progress, many fascinating questions remain open. Can we predict a priori which pattern will form for a given set of experimental conditions? This is still challenging. How do systems transition from one pattern type to another as parameters change? The dynamics of these transitions are poorly understood. Most theory assumes identical bubbles, but real systems have size distributions. How does polydispersity affect collective behavior? Can we actively control and reconfigure these patterns in real time for applications? This is an area of active research. Let me summarize the key lessons from this remarkable story. First, classical linear acoustic theory predicted that bubbles would simply migrate to pressure nodes and remain stationary. Second, careful experiments revealed unexpected orbital motion and spontaneous self-organization into complex patterns. Third, the resolution came from recognizing that oscillating bubbles generate their own acoustic fields and interact through secondary forces. Fourth, near pressure nodes where primary forces vanish, these secondary interactions become dominant. Fifth, the resulting system exhibits rich, nonlinear collective behavior that emerges from many body interactions. This is a beautiful example of how nature surprises us and pushes our understanding forward. Even seemingly simple systems like bubbles in a sound field can exhibit unexpected complexity when you look carefully. Linear approximations, while useful, have fundamental limits. Real physics is often irreducibly nonlinear. Understanding collective phenomena requires moving beyond single-particle thinking to embrace many body interactions. And finally, curiosity-driven research into seemingly esoteric phenomena often leads to important practical applications we couldn't have anticipated.